Back with part 2 as promised. I'm not going to start with this number 2 that I said was the awful one. I will start with some of these. The thing about trig identities, and I've said this before, the thing about trig identities is not just knowing your replacements, but it's being good at all the other mathematical skills that you were supposed to collect from kindergarten to the end of grade 11. So if any of that stuff is missed, then things go a little haywire. I am going to choose to start to work with this one first, so I'm going to move it to a new spot and we'll work on it. I'm going to keep my thetas. I quite like them. I'm going to go back to red for fun. And I am not going to keep bopping back and forth between the replacements. You are going to have to figure out where that is, even though I will name the category. So I'm going to bop one time here. So your categories are reciprocal identities, quotient identities, and Pythagorean identities. So I will mention where I get them from, but I won't flip back and forth, back and forth, back and forth. So the first thing I need to tell you about is there's no way I'm taking the number 1 and turning it into sine squared theta plus cos squared theta. I'm not turning it into a Pythagorean identity. 1 is beautiful. It's not trig. I want to head there. When I get to, or back to the left side, which is actually where I'm starting, I notice that this is 2 fractions being subtracted. So I could do my little crisscross 1, 2, 3 thing to get myself a common denominator, and that would be totally okay. But off the top of my head, I kind of remember that these 2 are reciprocal identities, so I'm going to replace one of them, and these 2 are reciprocal identities, and they're also quotient identities on the second term, so we could use those if we want to really mess things up. I'm going to go with the sines and cosines are my friends. So the secant is this reciprocal identity, and then I'm going to divide by cos theta. And I'm also going to take the right side very right. Then I'm going to put down a plus sign, sorry, a minus sign, and I'm going to make it large. Then I'm going to take tan theta, and sines and coses are my friends, so I'm going to write that. And divided by, and I'm not writing down cotangent theta, I'm writing down its reciprocal identity. And no, you are not allowed to do this. And the reason is because this is a division sign, so you have to wait until it's multiplication before you start knocking out information. So let's do the division. So that's 1 over cos theta times the upside down minus sine squared over cos squared times the upside down. This I'm multiplying, so I'm multiplying across the top, multiply across the bottom, multiply across the top, multiply across the bottom. Don't do the 1, 2, 3 thing if you've already got common denominators. So I can actually notice that my denominator is already common and write it like this. And hopefully you recognize the numerator as one of the 9 Pythagorean identities. It's actually one of the first 3. So I get to replace that numerator and leave the denominator. And anything over itself is 1, which is sitting on the right-hand side. So I am done this question. Now, if you can do it in less steps and also convince me that you're actually doing real math, then that's great. I need to show all my steps because I need to make sure everybody can do what they need to do, and this is the easiest way I know how to. So the next question I'm going to choose is another fraction question, so I'm going to choose this one, just so that we kind of bulk together the skills. So this is question number 2 for me. And the reason I'm picking it is because it looks the most like this one, so we are keeping it together. It's 2 fractions being added or subtracted, which requires a common denominator. The beauty of this first question is that it wasn't sines and coses, so when I turned it into sines and coses, the common denominator happened naturally. When we do this question, you'll notice that it's already sines and coses. So I'm going to have to do that 1, 2, 3 thing right now and hope that in the end, I end up with things canceling out and end up with a 0 on the left because that's what's sitting on the right, and I'm certainly not messing with it. So the 1, 2, 3 thing. 1, multiply denominators together so you get a common denominator. Don't know how much room I need. I'm going to put the monomial first and the binomial in a bracket. I'm not choosing to multiply that out yet. I can do that at any time in the future. Next step, this direction every single time. So that's sine x times sine x, which is sine squared x. Plus sign before I forget. 3 is this direction. And because I don't particularly want to screw anything up, I'm going to take the denominator in a bracket and multiply it by the numerator in a bracket, not actually doing it quite yet. Next line. I could, if I wanted to, multiply this out, as I stated before, but instead, I'm going to multiply out the top and see what happens before I go and do something that might be unnecessary. So this plus sign means that I don't have to run a positive through because that's natural, and I don't have a number. So I'm just going to FOIL this out. So here is another example of something you do with letters and numbers that now you have to translate to trig. So cos x times cos x is cos squared x. Cos x times negative 1 is negative cos x. 1 times cos x is positive cos x. And 1 times negative 1 is negative 1. Still, I could do this at any time, or I could actually have an eraser and erase and go back at any time. So this cos x is negative and this cos x is positive, so that's 0 cos x is on the top. I see my Pythagorean identity sitting right here. And it's not being multiplied by anything, it's just sitting there, so that's 1. And then I've got minus 1 at the back, over, still haven't decided about my denominator. Actually, I have, because if I'm looking at what I've got in the numerator, it's a 0 over a non-zero, and a 0 over a non-zero is 0, and I'm done. So I never actually had to make a decision about the denominator. The right side is 0. Now, without faking any math, my left side is 0. And I'm done. Next question. I am going to choose this one. I know this looks very fraction-like, but the reason I'm not picking it is because there's no need for common denominators, because I don't have 2 terms here that need a common denominator, and I don't need 2 terms here. So this is a different kind of fraction question than this one, which had 2 fractions, common denominator, and this one, which had 2 fractions, common denominator. So I'm going to drag this one in Comic Sans over to a page on its own, and let's look at it. And it's another one of those questions where I really, really like the right side. Now I have to mess with the left side. And I'm not a good foiler in my head, but I do know those little 2's mean foil. So I'm going to write the first bracket down twice so I can foil. And I see me running out of room and running into the right side equals 2. So I'm going to hop down a line, put down this plus sign, and then do the same thing with the back squared bracket. So the exponent 2's are telling you, write it down twice and foil. So, green pen. Sine theta times sine theta, sine squared theta. Sine theta times cos theta is sine theta cos theta, all smushed together. Cos theta times sine theta, same thing, and it doesn't matter the order, so I'm going to be as consistent as possible. And finally, cos theta times cos theta is cos squared theta. And again, I see me running out of room, so here's that plus sign. And because I don't need to multiply anything through, I'm just going to keep writing. So sine theta times sine theta is sine squared theta. Then sine theta times negative cos theta is negative sine theta cos theta. Again, looking in the above, I'm maintaining my order just for fun. Negative cos theta times sine theta is negative another sine theta cos theta. And then finally, a negative times a negative is a positive, and a cos times a cos is a cos squared. So what's happening? Now remember, this is all strung along so that you have a giant polynomial with trig in it. Here's a positive sine theta cos theta. Here's a negative one, so that'll make 0. Here's a positive sine theta cos theta. Here's a negative one, so that'll make 0. I need this to be a little neater. Maybe you're not one of those people, but I am. It's hard to read my writing after I've slashed stuff out. So I'm writing this down, and this down, and this down, and this down. And then I'm looking at the right side, which I really liked to begin with, and see if I can head there. So how can I get this untrig and turned into a 2? Well, hopefully you notice that here is my favorite being added and subtracted, no multiplying, so that is 1. And then here's another one, also not being multiplied, with a plus sign in between. And last time I checked, 1 plus 1 is 2, so they match. And I'm super happy. All right, 2 more. Let's take a look at this one. Now, I am hand cramping, so remember what we have left. This one and this one. So I am going to take a couple minutes break because my hand is cramping around this pen pretty badly, so I shall return. So a couple of things, hand cramp gone, a couple of things that make trig identities easier to prove left side equals right side with is knowing your identities and also practicing identities and trying things out. So being unafraid to make an attempt to do proper math and then to regroup if that method doesn't work. So you may have to restart a strategy. Another thing is knowing all those basic skills and doing a whole bunch of questions so that you look at a question and go, okay, I tried this strategy once before, so maybe I should try it again. If the first time you try trig identities is in the middle of an assessment, then you have nothing to compare it to, in which case you've done yourself some damage, because nobody thinks trig identities are easy. Some people think they're fun. I actually think they're not bad because I like playing with them, especially when they say prove and not prove if possible. So with this question, I don't think that this is an easy question. I think it's got a whole lot of skills that make it easy if you get the right strategy. But I'm looking at this and I'm thinking, oh my goodness, I've got cos x to the 6th and sine x to the 6th. And on the other side, what I super notice is that it's all sines. So if it's possible to take this side over here and turn it into all sines, I might get to the right hand side. So I'm going to take a guess and leave my right hand side as it is and hopefully head in that direction and be successful in getting there. So now the left hand side, and I'm actually going to do it in red just so in case I go so far. Something I notice about the left hand side, and you're going to roll your eyes or swear profusely, it's a sum of cubes. So that takes us back to factoring. And yeah, you need to know how to do common denominators, you need to know how to factor, you need to know how to FOIL. There's a whole bunch of stuff you need to know, and it's all that stuff from K to 11. So I noticed that this is a sum of cubes. A sum of cubes meaning, and I hope I've got my spacing right, a binomial size bracket and a trinomial size bracket. So I originally had my left side sitting here, and I moved it down so I have space. And remember where I'm heading. So if you cube root this, which is entirely possible because 6 is divisible by 3, you will get cos squared x. So cos squared x times cos squared x times cos squared x is cos to the 6th. And then if you do the same with the back, that's sine squared x. You take the first term and you square it, meaning you get cos to the 4th x. You can take the back and square it, so you get sine to the 4th x. Okay, that's a good thing. And then you take the two terms and put them into the center. You go back to the original question, keep it, change it, always plus. Now one thing I noticed that's really good is sine squared x plus cos squared x is equal to 1. So that quantity there is equal to 1. So I don't even have to write it down anymore because it's 1 times something. So that's very good. So let's focus our attention on this bracket right here. And like I said at the beginning of this question, we've got all sines here, so I need to get rid of my coses. And by getting rid of my coses, I don't mean just ignore them. I mean get rid of them mathematically, or hope that they get rid of themselves mathematically. So before I go on to too much math, I'm going to tell you that cos to the 4x is cos x squared times cos x squared. And then the second term, I'm going to leave alone for a sec, spread it out a bit because I do have some space, and my third term is this. So I'm happy with this one because it's all sines, and at least it has something to do with the right hand side. I'm not so happy with this one because it has sines and coses, and I'm really very unhappy with term number 1 because it's all coses. So what I have to do is I have to replace the coses, and fortunately they're cos squareds, so that means you can use one of your 9 Pythagorean identities. Aren't you happy I gave you a resource sheet? Then this sine squared x is going to stay, and this cos squared x will turn into its identity, Pythagorean. And then this guy is going to stay exactly the same as it is. So now I'm going to take this stuff and I'm going to multiply it out. So my right side is off. I have no way of checking yet. 1 times 1 is 1. 1 times negative cos, 1 times negative sine is negative sine. Oops, it's squared. And I have to remember the x. Then I have negative sine squared x times 1. Then negative sine squared x times negative sine squared x is positive sine to the 4th x. Okay, that makes me happy because I have another one to join with this. Then, very carefully, I have to multiply this bracket out. It's not going to take FOIL, but it's going to take me remembering this sine squared x is negative. So negative sine squared x times 1. And negative sine squared x times negative sine squared x is positive sine to the 4th x, and then plus the other one that I'm not messing with. So I've done a really good job of trying the strategy of taking something that had sines and coses, which is right here, and turning it entirely into sines because I could. And now, if I look at this, I've only got numbers, yay, sine squareds, yay, sine to the 4ths, yay. So I need to collect like terms and hope that it turns out to be what I just covered up. So numbers first. 1 is 1. Sine squareds. There's a negative sine squared. There's another negative sine squared, sine squared x, and another negative sine squared x. So that is actually negative 3 of them. Exponents don't change. And then here's a positive sine to the 4th x, another positive sine to the 4th x, and a third positive sine to the 4th x. So that's actually positive 3 of these sine to the 4th x's. Okay, drum roll. Let's see if I can do it. Not very good. That's why I'm not a drummer. Yes! 1 minus 3 sine squared x plus 3 sine to the 4th x. Whew! My strategy worked. And sometimes it does not work, and then you regroup. Okay, time for a little embellishment. I'm not just happy, I'm very happy my strategy worked. Okay, time for this guy, the last one. So I would love to be able to tell you that you can do that multiplied top by bottom, but you can't because that's not what trig identities is all about. So what I'm going to do instead is I'm going to rewrite the question, even though I like the x's. There's 2 ways to do this question. I'm only going to do one. But I'm going to put the left side here. On the left. And I'll put the right side here on the right. And the reason I show this question is so that someday you look at another question and it triggers your brain to think about this one. So this is part of the practice, even though I'm working through it with you / for you. So what I notice about these is that, first of all, it's all sines and coses, so that approach kind of fails because I can't fix anything. It's all friendly, but at the same time, it's unfriendly. So what you can do is another strategy besides looking at a question and saying, oh, one of the sides is all one word, so I'm going to try to make the other side be that one word. That's not going to work in this question. One other strategy, other than making it all one word, common denominators, factoring, distributing, and foiling, all that stuff, another strategy is to just force it into play. And so I look at this question and I think to myself, you know what? What I really want on the left side is I want a sine x on the top. But if I put a sine x on the top, that forces me to have a sine x on the bottom, because this quantity right here is just the number 1. So I've done no damage, except I've forced this to happen. I've forced a sine x on the top mathematically correctly. Gotta fix that. The other option, which I'm not going to finish off with, is to look at the right side and say, okay, what do I really want? And on the left side, I really want there to be a sine x on the bottom. So that forces me to put a sine x on the top, because that's just 1. Now, so there's 2 ways to do the question, and it just happens to both be an example of placing sine x's, not always sine x for your choice. So what I'm going to do now is I'm going to multiply stuff out. So for instance, and remember I'm heading looking for this, so as soon as I get there I should be good. Okay, so 1 plus cos x multiplied by sine x, and yes, I could multiply that out if I wanted to, but remember I'm heading for this, so I like that. And then in the denominator, I'm going to call it sine squared x, because I am not close to that. So next thing is I'm going to leave 1 plus cos x and sine x. And something you have to know is sometimes you go backwards and make things worse. So I'm going to take the Pythagorean identity for sine squared x and make it worse. The reason is, every time you have a minus version of any of the Pythagorean identities, you've actually created for yourself a difference of squares. So hold up while I write down the numerator, and then I'll talk you through the denominator. So a difference of squares is 2 pieces of information, 1, 2, both of them square rootable, separated by a minus sign, so you will have conjugates, 1 plus, 1 minus. And the beauty of that is that here is a 1 plus cos x on the bottom being multiplied, and here is a 1 plus cos x on the top being multiplied. So what we end up with is a sine x on the top, which I realize way back at the very beginning I forced into place with this. On the bottom, I no longer have 2 pieces of information or 2 brackets. Instead, I have just 1 minus cos x, and if I uncover that bubble, they are exactly the same pieces of information. So I have achieved what I want to achieve with the worst strategy of the bunch, and that is the forcing things to work out because you want it to be. Okay, last strategy to use. It doesn't happen very often. Usually it's just gearing out some math that you should already be comfortable with. So that gives you a little bit of a boost, and I know they aren't in order, but I'm going to start at the bottom here. Remembering that you can FOIL and collect like terms. Remembering that you sometimes might need a common denominator. Sometimes you might have to do some inserting, and that's it, from your list of 17 identities. We'll be doing more later. Remember, there are 28 or 29 of them. More foiling, more collecting, more replacement, strategy of looking at both sides and saying, what do I need? And also factoring. So there are some factoring questions. You do have to recognize it. In case I haven't mentioned, because this is, I'm going to say my first note for the trig identities unit. I told you there was factoring in every unit in this course. I'm still not lying to you. There's factoring in every unit of this course. You may need to ask for a little bit of help, and I may need to give it. So don't be afraid to ask, because that's what I'm here for. So still keep working on your trig identities. This was just a part 2 to take care of some questions. So there you go. Bye for now.